This video is for ELEC 1510 Logic Design. This is Lecture 22, Video 2 on Synchronous Counter Design, corresponding to textbook section 6.4. Synchronous counters are different than ripple counters in that we don't use the outputs from the flip-flops in the counters as the inputs to the clocks of other flip-flops. Instead, all of the flip-flops have the same clock connections, and we use the outputs from certain flip-flops as the inputs to the other flip-flops. We don't really have an input in this case. The only input is the clock, and the counter will cycle through its states based on its current states and the connections to the flip-flop inputs. So let's look at how we would construct a BCD counter this way. This will operate exactly the same as a ripple counter, but is just designed differently. So, for example, if we're in present state with 4 flip-flops, 0, 0, 0, 0, the next state on the clock edge is going to be 0, 0, 0, 1. We can have an output as well. In this case, the counter does have an output. It's going to be 1 if the present state is a 9, BCD 9. Otherwise, it's a 0. These don't necessarily have to have outputs, but they are state machines, so they can have outputs anyway. When we look at the transition from the present state 0, 0, 0, 0 to the next state 0, 0, 0, 1, we can assign T flip-flop inputs to control that transition. The first 3 bits don't toggle, but the last bit does, so we have 3 zeros and a 1. In the next state, we have 0, 0, 0, 1, which transitions to 0, 0, 1, 0. The last 2 bits toggle, so in this case, the flip-flop inputs would be 0, 0, 1, 1. For all of the remaining transitions, you can determine what the T flip-flop inputs need to be, and then based on that, you can assign logic functions using K-maps to those T flip-flop inputs. So what this BCD counter constructed using T flip-flops would look like is we have a single T flip-flop here. This is going to be number 8, so corresponding to this column. The output we're going to call Q8. I'm going to call the input T8. In the table, it's called TQ8. I think it's more appropriate to call it T8. And T8, when you optimize it with a K-map, is going to be equal to Q8, Q1, or Q4, Q2, Q1. Okay, so then we have flip-flop number 4 with output Q4. We have input T4, and T4 optimized using a K-map is Q2, Q1. Then we have T flip-flop number 2 with output Q2. The input T2 is going to be equal to Q4, Q1, or Q8 prime, Q1. And finally, flip-flop number 1 has output Q1 and input of T1, which in this case is always a 1, as you can see. So we could draw that as a better logic function. Here I've just drawn it as the actual Boolean expressions. We could draw that with circuitry, and that would produce the binary counter as well. All right, so let's discuss a few extra types of counters. The first is going to be called a ring counter. A ring counter's behavior is that you have a single 1. So let's say that we start off in a current state where we have a single 1 in the output of Q1, so that produces 0, 0, 0, 1. The next state is 0, 0, 1, 0. Then from that current state, we move to 0, 1, 0, 0. So basically, if you were interpreting this as a binary number, you'd be doubling the binary number every single time. Then finally, we get to 1, 0, 0, 0, and then it resets to 0, 0, 0, 1. So again, you could go through and assign T flip-flop inputs or JK flip-flop inputs, or even D flip-flop inputs, and construct the counter that way. One caveat to this is that in Quartus, the flip-flops always start in a state of 0, 0, 0, 0, which means that you would be governed by the don't care conditions, most likely. You would probably want to introduce circuitry to reset it into this state if you were to get it to behave properly. Otherwise, we could design a ring counter which has an additional state of 0, 0, 0, 0, and then that would also work properly in Quartus. Another type of counter is called a Johnson counter. This one just has a different behavior. We start off in 0, 0, 0, 0 and move to 0, 0, 0, 1. Then from 0, 0, 0, 1, we move to 0, 0, 1, 1. And so basically from there we go to 1, 1, 1, then 1, 1, 1, 1, and then 1, 1, 1, 0. So at first in these steps we're filling in ones, and then in these steps we're filling in zeros. So you can see there's kind of like 4 ones that get shifted around in a circle, and 4 zeros on the opposite end of that circle, and you're just seeing half of that 4 ones or 4 zeros at any time. So this behavior is what we would call a Johnson counter. So now let's look at the design of certain very simple synchronous counters. I'm only doing 3-bit counters just to simplify this as much as possible. So let's look at a 3-bit ring counter. If we start in state 0, 0, 1, we move to state 0, 1, 0. Next, if we're in that state, we move to 1, 0, 0, and from 1, 0, 0, we move to 0, 0, 1. And so on every clock edge, we just rotate through those 3 states. Now, as I mentioned, in Quartus, we start off in state 0, 0, 0. So if you wanted to design something like this in Quartus, you'd need to add a state 0, 0, 0 in there somewhere. Otherwise, you would probably be governed by the don't care conditions, which would send you off into random states. If we just use D flip-flops to design this, then we have D4 equal to Q4, D2 equal to Q2, and D1 equal to Q1. And you can just compare the columns for the next states and the columns for the current states, and the assignments are fairly simple. D4 is going to be Q2, D2 is going to be Q1, and D1 is going to be Q4. That means that the counter looks like this. The only input, again, is the clock, because on every clock pulse we just rotate through to the next state, and the outputs are given here. This could also be designed using T flip-flops or JK flip-flops, but as you can see, the implementation using D flip-flops is fairly simple. So now let's look at a Johnson counter, a 3-bit Johnson counter. Again, this is where you start off in all zeros, and then you start filling in ones until you get to all ones, and then you start filling in zeros until you work your way back to all zeros. Now, the states for this are almost exactly the same as the ring counter except for D1. So D4 again is Q2. You can just compare the next state and the current state to see that equivalence. D2 is going to be Q1 and D1 is going to be Q4 prime. So the only difference between the ring counter and the Johnson counter is D1 is Q4 prime rather than Q4. So the implementation looks like this for that 3-bit Johnson counter. Again, the only input is the clock. The clock controls when we move through the states. And the outputs are given here, and it'll rotate through all of those states. In general, the implementations that you see here can be extended to higher number of bit ring counters and Johnson counters.